All right, welcome to WebAssembly and Containers. To get things kicked off, let's just kind of take a moment and relax and play a little game. All right, this is Finicky Whiskers. Let's get started here, start a new game. All right, now I need to feed Slats the cat. She's hungry. She'll tell me what she wants. She's thinking chicken. Now she's thinking veg. Oh, now chicken again. And the faster I can click, the higher my score is going to be here. Oh, beef. All right. Not veg. That one's particularly hard because it's one side to the other. But the counter's counting down, and I'm not doing terribly well. Oh, some more beef. All right, almost done. And back to beef. Chicken. Chicken. All right. Well, that was not too bad. I didn't think that was going to be a terribly good game, but that worked out okay. All right. Well, you probably didn't come here to watch me play games all day, so I should start by introducing myself, and then we'll dive into WebAssembly and Containers. My name is Matt Butcher. I'm at Fermion. We're building what we think is the next wave of cloud computing, and I'll talk a lot about that today, but we think WebAssembly plays a very big role in kind of this next generation of cloud computing. You might have seen me around. I'm very passionate about containers, virtual machines, the compute ecosystem. I worked on OpenStack many years ago. More recently, I worked on a wide variety of container technologies, including I created Helm and Brigade and some other similar projects. These days, though, I'm really fascinated with WebAssembly, so I'm really excited to talk today about where I think compute technology is going. Now, this one time, a guy said a thing on Twitter, and you might be surprised to learn that maybe it got taken a little bit out of context. Solomon Hykes, the creator of Docker, tweeted at one point, if WebAssembly and Wasm had existed in 2008, we wouldn't have needed to create Docker. Well, this particular quote has gotten, as you might imagine, a lot of traction. I mean, it got about 800 retweets, couple thousand likes, and I've seen it quoted in probably 30 plus blogs and articles and so on. But really, to gain the full context, you kind of need to read what he said afterward. Because the next tweet he said, so, is WebAssembly going to replace Docker? No. And then he lapses into narrator voice, right? But imagine a world where, Docker and WebAssembly are working together. And that's what I'm going to talk about today. I don't think that WebAssembly is going to defeat Docker in any particular way. I think that's sort of a nonsensy way of looking at things. But I think that it is going to come into play in very interesting ways in combination with Docker. So the logical place for us to get started is to define our terms, right? Let's talk about cloud compute. Cloud compute is distinct from storage or from networking because cloud compute is really about taking something, your thing, and being able to execute it somewhere else. And in particular, we tend to talk about these things you want to execute as workloads, right? So a workload is executed inside of some environment, which we call an execution environment, that is isolated from its host operating system, but that the host operating system will strategically expose certain facilities that the workload needs in order to get its job done. Or if you want a really high-level generic way to talk about cloud compute, it really goes more like this. It's a generic service for me running my stuff on your hardware securely. Right. And so when we talk about cloud computing, we're talking about sort of a category of different kinds of ways to execute these sort of generic applications on somebody else's hardware. One that I'm sure you are familiar with is virtual machines, right? Virtual machines are sort of like the workhorse of the cloud. I also think of them as sort of like the heavyweight class of cloud computing because they package up the entire operating system from kernel to drivers up through the file system, all the supporting things up to your application code and then and your particular data. And it all gets bundled together in this giant image file. Because they're big, and when we talk about big, we're talking about gigs and gigs usually, their startup time tends to be slow, measured in minutes, but they're kind of, like I said, they're the workhorse. They're the ones this is the technology that is behind so many other things, right? Drives so many other things. Now, I used to think when I, made my transition from working on OpenStack into working on containers, I mean, it was a very exciting time, right? And I just absolutely fell in love with containers. But I used to think that containers were in some way going to defeat virtual machines, that somehow there was some kind of existential battle going on and that only one would survive. This is what we would call zero-sum thinking, right? That there has to be a winner and there has to be a loser. However, if you look at the ecosystem today, what you'll realize is that not only has container technology, totally taken off and done remarkably well, but virtual machines too have been growing. So clearly there was no zero-sum game thing going on because both of them have survived. And that made me realize that the reason for this is that each has its niche. Each solves a particular set of problems. And it doesn't really make sense to try and replace one with the other. You need both of them, but each one does kind of a different thing. Which got me thinking, all right, so containers are not necessarily the heavyweight class of cloud computing. They're sort of like the middleweight class of cloud computing. Their image sizes aren't measured in gigs, typically. They're usually measured in tens to hundreds of megs, right? Startup time isn't measured in minutes, it's measured in seconds. It only takes a couple of seconds to start up a Docker container. And where it really sort of hit its niche is that it is super easy to build Docker images, right? You just write this Docker file, it packages up your application and all the files that it needs, but it doesn't need stuff like the kernel or the low-level drivers or all those sort of supporting things. It just needs the stuff you need in order to execute your particular workload. So that then got us thinking, so there are clearly two classes of computing, one that's kind of heavyweight and one that's kind of middleweight. Is there room for another category of computing? And in particular, we were running into some specific problems that we were having a hard time figuring out how to solve. We needed one binary file that could be executed on lots of different architectures. We needed smaller image sizes that we can move around the cloud faster. And more than anything, we really needed something that could start up, execute, and shut down really fast, like instantaneously. And so as we got to talking through these things, we went, okay, so there's virtual machines, the heavyweight class, containers, the middleweight class. We need to find somebody with something with those characteristics to be our new lightweight class. So we looked around, and of course there are a number of technologies out there, but the one that caught our attention as the most promising was honestly a little bit surprising, because it was WebAssembly, and WebAssembly was built for the web browser. But we looked at it and we went, oh, the characteristics that make it great for the browser also make it really great for the cloud. For example, and here's a couple of them, right? The cross-platform, cross-architecture story. Gone are the days when you would even tolerate visiting a website and it saying, sorry, you can't view this website unless you're running Windows with IE on it, right? Or unless you're running Safari and macOS. We want cross-platform, we want cross-architecture, and WebAssembly was built with the intention of filling that cross-platform, cross-architecture story for the browser. Now, we want that on the cloud as well. We want to be able to choose ARM or Intel or Windows or Linux or Mac or any other bespoke operating system, but we don't want to keep having to rebuild our binaries or our images or whatever to run on each of those. We want to compile it once and then just push it off into the cloud, and regardless of what the cloud schedules us onto, our binary will run. Now we got a couple other concerns that were interesting for the browser, interesting for cloud. One is that in the browser, users have a very low tolerance for waiting. I know, shocking, right? Users want to see their thing right away. They want to click on a link and the web page to load. And as soon as you hit, 50 to 100 milliseconds, people start going, come on, and get impatient. Now that requires a couple of background features to your technology. The first one is, since data is getting moved across the network, you need that data to be fairly small so it can be moved quickly across the network, so small binary sizes. But you also need fast startup times because nobody wants to wait there while the virtual machine starts up and loads a language library. And so WebAssembly was really built to meet that particular feature set, that goal of being able to give the user high responsiveness, high speed. But those were exactly the same features we really wanted in our cloud side solution, that we said we really want to be able to start up and shut down these microservices as fast as we possibly can. Now, the last one that I put on here is probably the most obvious of them all, right? When you go visit a web page, you don't want to run the risk of having somebody run something malicious that roots your box, right? Security sandboxing in a web browser is of paramount importance. And likewise, in the cloud, you don't want to have your customers deploy something into your cloud and then have them have the ability to root the cloud and break out and get into each other's data, right? So security sandboxing is something that is necessary for both of them. And so as we looked at these things and the features of WebAssembly, we went, oh, this is great, because what we see WebAssembly offering is just the kind of stuff we wanted for the cloud. But there was one more piece that we really needed. In a browser, WebAssembly might interoperate with the document object model, right? The HTML, the CSS, might work on some images, might interact with some JavaScript. In the cloud world, though, that's not really what we care about. Instead, in the cloud, we want it to be able to interact with things like the file system securely, right? To load in the files it needs, environment variables to get configuration information, or even things like the system clock, because we want to make sure that if we're running several on the same system, their clock is all set to the same thing. So we looked around to see if anybody else had done work on this, and were once again pleasantly surprised to discover that W3, the standards body that does HTML and CSS and WebAssembly, was also standardizing the WebAssembly System Interface, or WASI, which was going to define all those little bits and pieces that we needed in order to do this stuff. WASI has since then sort of matured and also caused several other new specifications to branch off. And what we're seeing is the working groups that are working on these things, which now includes Fermyon, very intent on building the right fixtures that we would need to build cloud computing platforms that use WebAssembly. So it's a very, very exciting time to be involved in this technology. So we took all of this information and we decided to build some projects, built several different projects using WebAssembly and cloud context, including trying out containers and doing some really low-level stuff. Ultimately, what we realized was we needed to build something that was going to make it really easy for developers to assemble WebAssembly applications. So a good development framework that could help them build microservices and web applications rapidly. And so a couple of weeks ago, we introduced Spin, which is Fermyon's execution environment for running WebAssembly modules. It's all open source. You can take a look at it at github/fermyon/spin. But I could go on and talk through the technical details of Spin. Trust me, I actually really want to do that. I could probably fill out another 15-20 slides of that. However, I thought it might be a more fun way to look at that and how it interacted with Docker by returning to our game and talking a little bit more about Finicky Whiskers. You see, Finicky Whiskers is actually backed by a bunch of WebAssembly code and some Docker containers. As we play the game, we're basically getting a glimpse into what this, third wave of computing might look like. Because the game is composed of three distinct categories of stuff. The first category is it's got that web front end where we were, the cat and the screen and the clicky buttons and stuff like that. That's all HTML, images, JavaScript, CSS, that kind of thing. It's all getting served to us from the cloud via a WebAssembly module, but that's just kind of the local code that we're running in the browser. Now, backing this in the cloud are 8 different WebAssembly microservices. Today we're only going to talk about 5 because the other 3 are not necessarily gameplay, but things like leaderboards and stuff like that. But there are 8 WebAssembly modules all running in the cloud that are providing the backend for this game. And along with them is Redis running as a container. So these modules then use Redis to communicate with each other as things are happening during the course of the game. So as we get playing the game and we're clicking on these buttons, chicken, 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 fish, 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 right? We're executing HTTP requests that are getting routed back to Spin, which is saying, oh, this one goes over here, this one goes over here, that one goes over there. And it's starting up, executing and shutting down those WebAssembly modules nearly instantly to handle each and every one of those requests. So when I first load that first web page, it goes up and it says, hey, need index.html, starts up a module, returns back index.html, shuts down the module. And it does that for each of these requests that we're generating. And so as we're playing and we're clicking on the buttons, the faster we click, the more WebAssembly modules we're starting. And the more that we can do there, the greater the load, the greater the burden on the cloud architecture that we've got running behind it. So in a silly sort of way, we like to talk about Finicky Whiskers as the world's most adorable manual load generator, because that is essentially what it was designed to do. So let's take a look at how it does that, right? So here are those 5 modules I said we were going to cover together with the Redis running inside of a Docker container. Now, when we first load the game, right, and as you noticed, it was nearly instantaneous to load. But what's going on behind the scenes is my browser contacts Spin and says need index HTML. Spin starts file server. That file server returns back index HTML and shuts down, okay? Then the browser parses that and says, oh, I need these files and these files and these files. It takes around 30 files to load to get Finicky Whiskers running. That's images, CSS, JavaScript, HTML, all of those things. And every single one of those requests is starting and executing a new WebAssembly module to completion before exiting. Now, again, the load time for this was nearly instantaneous, right? We run these things routinely through the Google scoring mechanisms and routinely get 99 to 100% on our score. That is, we get perfect scores for the speed of these particular WebAssembly modules. Now, after I've done that, then in the browser, I see that start button. I click the start button, and that goes off again to Spin, which starts up the session module and creates a new session for us. Now I've got a 30-second game session, and the cat is hungry and is starting to demand food, and I'm starting to click on that button. Fish, 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 chicken, 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 veg, 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 veg. Each time I'm clicking, I'm sending another HTTP request that's running another WebAssembly module, again, starting it up, running it to completion, exiting. But that WebAssembly module is merely validating the data that I sent. And then it pushes that data into a channel on a Redis pub sub. And listening on the other end of that is another WebAssembly module. And each time a message comes through, that module starts up, parses out that message, tallies new scores, and puts the new scores back into Redis's key value storage. And then it exits, right? So over and over again, every time I'm clicking on a button, I'm executing the first tally module, which is sending messages into PubSub, which is then executing the morsel event module, and then that's going back and updating Redis again. Now, periodically, you probably notice there's a timer ticking down, and each time the timer ticks, the scoreboard gets refreshed. Once again, another WebAssembly module running in the cloud that is going to Redis, fetching that value out of key value storage, and then displaying the score on my scoreboard. So, as you can gather from this description, it seems that we might have invoked a whole lot of WebAssembly modules while we were doing this. Again, world's most adorable load balancer. So the file server gets loaded somewhere around 30 times. The session, it only gets once because you only use it at the start of the game. And then the tally module is going to get executed every single time I click the button. So hypothetically, if I score a perfect game, I will invoke 100 and some tally events that'll each result in 100 and some events that go on to Redis. And so that's another 100 and some, invocations there too. So just by clicking the buttons, I'm running, a couple hundred WebAssembly modules. And then again, as the timer ticks down, every tick, it calls the scoreboard module again, sends a new request to the cloud, which starts up the scoreboard. So we get about 30 requests for the scoreboard during the game, and then one final 31st request. So in the end, we have about 262 separate WebAssembly module invocations happening during that 30-second interval. Once again, Finicky Whiskers is a load generator. So with that in mind, let's play again, and let's see some of that load by looking at the backend. All right, now let's play Finicky Whiskers again, and this time you can see my Docker execute on the Redis, so you'll be able to see some activity happening there. So let's restart. All right, we're straight off with vegetables. You should be able to see all kinds of things going on the terminal there as I try and click frantically away and feed the cat. Chicken, chicken. And you'll notice if I miss, then you'll see a different set of events on the panel than if I'm doing quite well. Almost done here, down to the last third. Oh, come on, click faster, little mouse. Chicken. And there we go. So our time is out. And now we can see on this terminal here, there were a whole bunch of publish messages, some gets, some sets. What you're seeing on this terminal is Redis as I'm publishing messages in for every single click, and then the scoreboard module, the morsel event, is reading that, parsing it, and then updating the score with the latest score. And so you can kind of see that all going on in the background there, which in the end results in showing that scoreboard at the end. So we played Finicky Whiskers a couple of times, and in between we've kind of seen how the application was architected. Right now, it's important to say that Finicky Whiskers was not intended to be like the best possible architecture that we could build for a gameplay or anything like that. It is intentionally built to illustrate how WebAssembly and Docker can be used together to build an application. And so for that reason, where we possibly could have written this game to be entirely client-side or something like that, that wasn't the point of Finicky Whiskers. The point of Finicky Whiskers was really to demonstrate the potential of this particular combination. So let's talk now at a little bit of a higher level and say, okay, so how did we use these pieces and why did we use them this way? We used WebAssembly to create this kind of microservice architecture where we're rapidly starting and stopping each microservice to handle a request, right? So a microservice starts, performs the request, and then shuts down. Now, in this case, we have to build an application such that it can complete a very simple task. So this is a great way to build highly compact, highly scalable microservices. And this technique is good for keeping resource utilization down, right? Now, if we think about the way we often run services, we'll run a web service and we'll leave it running all the time. During peak hours, we might see utilization pushed up to 70, 80, maybe even 90%. During off-peak hours, we still see the application sitting there consuming CPU and consuming memory as it sits idly, maybe not even answering any requests at all. In the WebAssembly world, something is only running when it's responding to a request. And so in this case, when there are no requests coming in, then the application essentially scales down to 0. And Spin just sits there watching for new connections, and if a new connection comes in, then it starts up the appropriate microservice again. But the flip side of that is also interesting, because Spin will scale WebAssembly modules up very rapidly. So if we suddenly get slammed, like when the Fermion.com site got hit by Hacker News, we went from 5, 10, 15 simultaneous requests up to 90, and then up to, at one point, up to the 2000s. And yet all of those, essentially it's scaling fairly horizontally in our setup using Nomad, scaling fairly horizontally just enough to handle the load. And then as the load starts to drop off automatically, all the WebAssembly modules are scaling back down until ultimately, if they're at rest, they scale all the way to 0. So WebAssembly ends up being a really good and compelling story when speed and resource utilization and rapidly scaling up and down is a kind of thing that you're concerned with. Now, I should point out that one of WebAssembly's current kind of weaknesses is that it's very difficult to take existing code and simply compile the whole application to WebAssembly and assume that it will run as a Spin microservice. For the most part, at least at this point in time, writing WebAssembly is greenfield. You will want to go in and read the Spin docs and build something that handles it. And they're very easy to build. They work following the request response pattern that you see in Go, in Rust, in JavaScript, in the Node.js world and elsewhere. Now, we also used Docker, and we used Docker because of its strong point in being able to run longer running services that do stay up all the time. Redis is a good example of this. We don't want our Redis system bouncing up to handle an incoming request and then shutting down and then bouncing back up again to handle a new incoming request, because it would be losing or having to reload all the data that's important to us. In that message queue example, we wanted Redis to be there so that when a message came in, it could pop the message into the channel. And that when something else came online to read the message, it can immediately hand that off to that other thing. For the key value storage, we wanted that data to persist for longer periods of time. We don't want our keys and values disappearing or having to be reloaded from disk or something like that every single time they're requested. So Redis really showcases how we're using Docker because it's great for long-running processes, for pieces with predictable loads, right? When you don't need to necessarily scale up and scale down very quickly, but can say, okay, I know I need 3 Redis instances, and I'm always basically going to need 3 unless, load gradually picks over time, up over time, and then I might add a 4th one, and so on. So very different use cases, but as we've seen here, both of them have their strengths, and when they're combined together, you can build some really fun and interesting applications. With that, if you want to go play Finicky Whiskers, you can head to the finickyWhiskers.com website and generate some Finicky Whiskers food load right there, test out our stuff. But if you want to get started with Spin and take a look at how things are architected when you're using Spin, spin.fermyon.dev is our documentation site, and github.com/fermyon/spin, you can just dive straight into the source code. If you want to watch from a distance or chat with us, fermyon.tech or Fermyon Tech on Twitter is the thing to follow, or you can join us in Discord. Just go to fermyon.com and find our Discord link there at the bottom and click on it and join us. We're happy to discuss this stuff. With that, I think it's game over. Thank you very much.